Hi. Since we started this group in 2019, I don't recall any discussion of forecasting. I think we should pay attention to it because it's a field that's evolving as fast as the IIoT, sensors, or digital twins. Let's start with a somewhat embarrassing personal experience with forecasting that motivated me to take a closer look. In 2009, I was working with an aircraft manufacturer that wanted to compete with the Boeing 737 and the Airbus A320. They needed a long-term forecast, and their press sheet didn't look to me like it was based on data. So I plotted the history of the sales of the 737 and the A320 since 1967, not knowing what to expect. The charts for both planes appeared to show 3 to 5 year boom and bust cycles. I advised my client to anticipate such cycles going forward in planning their supply chain. Revisiting the same series 10 years later, however, I was stunned by how mistaken I had been. It was a mistake in 2010 to assume that the 3 to 5 year cycles would continue. It would have been a mistake in 2019 to assume that the growth of the previous 5 years would go on forever. The chart is insufficient as a basis for long-term capacity planning. Does it even make sense to place data from 1967 to 2019 on the same chart? The products have kept the same names as outer shapes, but everything else has changed, from the engines to fuselage materials and cabin equipment. Meanwhile, the world's population has gone from 3.5 billion people in 1967 to 7.8 billion in 2018. The cycles through 2010 are related to the general economic growth and multi-year delivery lead times. Airlines overbought airplanes based on their own optimistic sales forecasts. 3 years later, as the expected growth had failed to materialize, they had too many planes and stopped buying. Another 3 years later, the activity had picked up. The airlines were short of planes and overbought again. Why was this pattern broken? I asked an industry insider who said the business has changed on both the supplier and the customer side. The aircraft makers have reduced their order fulfillment lead times to 10 months, making it easier for airlines to forecast. In addition, the airlines have improved their own sales forecasts. So let's take a look at what's happened to forecasting. The Makridakis competitions are a means of tracking the evolution of business forecasting in general. Spiros Makridakis, from INSEAD in Fontainebleau and the University of Nicosia in Cyprus, has been organizing forecasting competitions since 1980. The frequency of these competitions and the number of participants has been rising dramatically. In M5, held in 2020, the challenge was forecasting the sales by Walmart of 3,049 products in 10 stores for 28 days based on a 5.5-year history of daily sales, supplemented by external variables like special days, weather events, and promotions. Methods from the 1970s like autoregressions, moving average, exponential smoothing, and Holt Winters outperformed AI-based tools until the M4 competition in 2018. They no longer do. In M4, as in M5, method that included an element of machine learning won. M5 was actually two competitions, respectively called the Accuracy Challenge and the Uncertainty Challenge. The more common terminology for this distinction is point versus probability forecasting. In the Accuracy Challenge, out of 100,000 submissions, the winner was Young Jun-yin, an undergraduate student at Kyung-hee University in Korea, working on his own laptop. The Uncertainty Challenge was won by David Lander from North Quay and Russ Wolfinger from SAS USA. Sorry, I couldn't find a picture of David Lander. Let's take a closer look at the distinction between point and probability forecasts and how it affects operations. On the top of this chart, you can see point forecasts. On the bottom, probability forecasts. A point forecast is an estimate of the mean, median, or mode of a future value. There is something logically questionable in using such a number as a forecast. Numerical variables never match it, and we call the difference between the actual value and the forecast a, quote, error, unquote. A random variable, however, will fluctuate around these numbers, no matter how perfectly estimated. That's why you call it random. No actual error is involved. In probability forecast, you estimate a distribution for the future value. It lets you make statements like there's a 50% probability that sales of product X will exceed 150,000 units next month. Or the probability that it will rain today is 25%. The real reason point forecasts have dominated the field is that probability forecasts require more computing power. It is readily available now, but it wasn't when the most common forecasting methods were developed. How do you tell whether a probability forecast is correct? You can divide each distribution into quantiles. For each point in the testing set, you determine which quantile of its forecast distribution it falls in and aggregate this information over the whole testing set. Then 10% of the points should fall in the first quantile, 20% in the second, and so on. The probability forecast we are almost familiar with is the weather report on the radio. If the weather forecast on the radio is it will rain today, it's a point forecast. If it says there's a 50% chance that it will rain today, it's a probability forecast. Making the point forecast is taking responsibility for telling listeners to pack an umbrella. The probability forecast, by contrast, gives listeners presumably objective information based on which they can make their own decisions. What is interesting about this case is that after the forecasters estimate a probability of rain, the announcers lie about it by overstating it. Why? They do it because fewer listeners complain when they needlessly pack an umbrella than when rained on without one. It's a case of asymmetric losses. In production, the planner can calculate the losses associated with underproducing or overproducing, weigh these losses with the probability forecast, and decide how much to make to minimize the expected loss. In manufacturing, you place an order for a specific quantity of parts, not a probability distribution. With the probability forecast, however, the materials manager can choose the risk to take. With a point forecast, the forecasters can make the decision, which really shouldn't be theirs. Their job should be limited to providing the best possible forecast, which is enough of a challenge. That is a fundamental way in which a shift to probability forecast can affect manufacturing operations. Today, I focused on one particular aspect of what's new in forecasting, the shift from point to probability forecasting. In fact, it applies only to residuals after you have estimated trends, periodic variations, and cyclical variations driven by supply and demand dynamics rather than time. There is more to forecasting than analyzing a history of sales, and external factors like natural disasters, wars, or fads strongly affect the result. There is, however, much less detailed data available about these factors. In addition, many products have a stop-and-go demand pattern that is another challenge. Forecasting is often not for an individual item, but for a family with positive or negative mutual influences, depending on whether products complement each other or compete with each other. Promotional giveaways complement a sold product, but the standard and luxury versions of the same product compete with each other. Sales is what we have data on, but demand is what we're after, and it includes sales by competitors as well as market trends. Finally, all of these developments are intended to meet the needs of businesses like Uber or Walmart, not manufacturers. Therefore, some thought is needed on adapting them to the needs of manufacturers. If you would like to dig into these issues further, you can start with a few blog posts that I have published in the past few months based on my own investigations. There are many books on time series forecasting. Among them, I recommended this one for its coverage of many of the advanced techniques. Rob Hindman from Australia has been a key contributor. I have just received a copy of Vanderput's book and can't comment on it yet. It's not a general book on forecasting, it's focused on supply chains, which is why I got it. Nicholas Vanderput is based in Brussels. Finally, Kaggle is a go-to site for free data science resources, including forecasting. It contains data sets to try techniques on, contributed software, and discussions. Kaggle also hosts problem-solving competitions organized by members. It's a Google subsidiary. Thank you for listening. Your questions and comments are welcome.